Hey, welcome to the video on electrical systems. The first thing to know for electrical systems is charge. Charge is the property of matter that causes it to experience a force in an electric field. Experience a force in an electric field. The only thing you need to know for charges in this topic is the symbol Q, the SI unit, coulombs, and that when these charges flow, when they flow, they produce what is called current. So this is the flow of charges, right? Due to the flow of charges, you have what is known as current. Current is defined as the rate of flow of electric charges, and the symbol is I, the SI unit is amperes. And before electrons were discovered, we assumed current to flow from the positive end to the negative end. So this is the direction that we are still using, and we call it conventional current. However, since electrons were discovered, we now know that current is actually supposed to flow from the negative end to the positive end. So we just call that electron flow. Okay, because this doesn't affect any real world behavior or computation results. Next, we have the equation for current. I is Q over T, because this is the rate of flow of charges. So Q is charge, T is time. So charge per unit time gives you the current. So amperes is also can also be represented as coulombs per second. Okay, next, this is a simple example, and after that we have the concept of EMF and potential difference. Both of these are examples of voltage. Okay, and the main difference between EMF and potential difference, PD, is that EMF is the work done by an electrical energy source to move a unit charge around a complete circuit, while potential difference is the work done in moving that unit charge between 2 points. So if the 2 points happen to be across the whole circuit, so between 2 points of, say, the battery, so from this yellow point to this yellow point, that would have covered the whole circuit, and so this would be equals to the EMF if you measured the difference in potential between these 2 points. If you measure the difference in potential between these 2 points, you wouldn't end up getting the EMF because it's not the whole circuit. So that's the difference between EMF and potential difference. EMF has to be for the whole circuit, while potential difference is between any 2 points. Okay, since both of these have similar definitions, the work done in moving a unit charge, they will have the same equation. The work done per unit charge is the voltage. So V is the work done per unit charge. Okay, so that's how you end up with V equals to W over Q. Okay, and again, the same similar simple example. Next are the ideas about ammeters and voltmeters. Ammeters are used to measure current because ammeter, another way to look at this is it's ampere meter. Ampere is the unit for current, while voltmeter is the voltage meter, and voltage is the volts meter, and volts is the unit for potential difference and EMF, so it's measuring voltage, right? Next, when you connect an ammeter, ammeters are always connected in series and voltmeters are always connected in parallel. The symbol is a circle with an A in the middle and a circle with a V in the middle. And one more thing to take note is that the resistance of an ammeter is given to be 0, and the resistance of a voltmeter is given to be infinity. Okay, we will cover the idea of resistance in a bit. After this, we have power. Power is how fast energy is converted from one form to another. So the rate of conversion of energy from one form to another is power. So because it's the rate of conversion of energy, it's how much energy is being converted divided by the time. So power is energy over time. And in electricity, we can also use the equation P equals to IV. And I've gone through the derivation of P equals to IV before, so I won't go through it again. And how bright a light bulb is depends on its power. So how much current and how much voltage is going through the light bulb will determine the brightness of a light bulb. And this is also applicable for other things. So for example, how fast the fan is spinning depends on how much current and how much voltage is passing through the fan. Or say how hot a heating element gets depends on the current and potential difference. Okay, next is the concept of resistance. Resistance is the ratio of potential difference across it and the electric current through it. So because it's the ratio, it is given as a fraction. In science, we always take ratio to mean a fraction of something over something, and in this case the first something, so the numerator will be the potential difference, the denominator will be the current. So that's how you end up with V over I, because you have potential difference across it, potential difference against a current. So R is given to be V over I. And this is one of the most important equations that we will be using in this topic, R equals to V over I. And from R equals to V over I, you're able to derive two other equations. So if you multiply both sides by I, then you are left with IR equals to V. So basically V is equals to IR. Next, you divide both sides by R. You're left with V over R is equals to I. So the second equation you can get from this is I is equals to V over R. So the three equations are V equals to IR, I equals to V over R, and the main equation where these two equations were derived from, R equals to V over I. Next, moving on to how effective resistance is calculated. So effective resistance, another word for effective resistance is net resistance, which just means how much resistance is in the circuit, so maybe total resistance, right? And there are two different types of circuits, series circuits and parallel circuits. If the resistors are connected in series, then the resistance is simply the sum of all of these resistors. So R1 plus R2 plus R3 will give you the total resistance of the series circuit. If they are connected in parallel, then you have to go through an intermediary step. So 1 over R, you have to calculate 1 over R first, and then take reciprocal on this 1 over R. So 1 over R will be equals to 1 over this whole thing here. And 1 over R will just give you R. So R is equals to 1 over this thing here, right? Next are some components that are represented by different symbols. So for example, an open switch is represented by this symbol, a closed switch is represented by this symbol, a variable resistor is represented by this symbol. Another word for variable resistor that you might see often is the rheostat. Right? They are interchangeable, they mean the same things. Basically, it's a resistor where the resistance is able to change. And next is the idea of a short circuit. So a short circuit occurs when you have an alternate path for current to flow with no resistance, right? So if you had two paths to choose from, Say you were at a crossroads and you have two paths to choose from. One path has lots of, say, lions and wolves. So lions and wolves. You would rather not walk this way because this way has high resistance, right? Instead, you want to choose to walk the other way where there is no resistance. And when there is no resistance, it's better for you to walk this way, so you would choose to walk that way. And same thing for current. If there is a path with high resistance, you would rather walk the other path where there is no resistance. And so the current will not flow through this way, but all of it will flow through this way. And when you have a short circuit in the whole circuit, then the current will become very high because all the current is going this way, right? And if an electrical component gets short circuited, this means that the component itself will not work because there is no current flowing through it and only through the rest of the wires. Okay, so if we go back to our earlier example of ammeters and voltmeters, remember how ammeters have zero resistance and voltmeters has infinite resistance. So this means that the current will choose to flow through the ammeter because there is no resistance. When it reaches this point here, even though it's in parallel, the current will not flow this blue path because of its infinite resistance. So the current will skip the voltmeter and all the current will flow through the resistor and just follow this yellow path instead. Okay, next, more on series circuits. Series circuit is one where there is no branching and they are all arranged on a chain one after the other. So current only has one path it can take. So current in a series circuit is the same. Why? Because there is only one path to take. So we can look at current as if it was a person that has to run errands, right? So this person has to run errands, so it has to go around this whole thing. So at every point, there will be this person because there is no alternate path to take. So if I have one person, there will be one person here, 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 and here. If I had two people, there will be two people at each point as well. So two people, there will be about two people here, 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 and so on, because there is only one path to take. Next, voltage in a series circuit. Voltage, you can take it to be something like these people having to run an errand, right? They have to spend money. So these two people run around the circuit. As it passes the first component, the component is something like a shopping center. So when you pass this shopping center, you have to pay some money to buy the things that you're running the errands for, right? So if you have, say, $2, so $1 here, $1 here, you have $2. You pay the first guy $1, and then you pay the second guy $1. So when you return, you're still left with the two people, but now you have no money left. Initially, you had the two people with $2, right? So the current is the same because you still have the same two people, but the voltage, the potential is different because here you have $2 and here you have $0. Why do you have $2? Why do you have $0? It's because you spent your money, $1 here and $1 here, right? And this only applies when resistance of R1 and resistance of R2 are equal. So assuming R1 equals to R2, then you would spend the same amount of money at each resistor, at each shopping center, right? So the amount of energy you use to get through the electrical component depends on the resistance of the resistor. Okay, next we have parallel circuits. In parallel circuits, we have branching. So when you have branching, there are different paths that the current can take. So the current will split. So remember, current is like people. So if I had two people here, when they reach this point here, one of them continues down this path, while the second person will continue down this path. Because there are two different paths for the two people to take, and assuming these two resistors have the same resistance, the two people will be split equally, so one person at the top, one person at the bottom. Next, voltage in a parallel circuit. So same thing, if they had $2, this person here would still have $2, and this person here would also have $2, right? This $2 is not shared between the two people, it's each person having $2. So when this $2, when you go through this resistor, you spend your money, so you're left with $0. You spend your money, so you're left with $0. So if you observe, this $2, which is the amount of money that they have at the start, is also the amount of money that you would have across each branch. Okay, and if the concept of having money is confusing, then simply, if you look at the numbers, say this was a 10-volt battery. So if it's a 10-volt battery, it means that the potential difference across the battery is 10 volts. So if the difference in potential is 10 volts, then on the positive side it should have 10 volts, and on the negative side it should have 0 volts, right? Because 10 minus 0 gives you a PD of 10 minus 0 gives you a PD of 10 volts. So if as it crosses the ammeter, remember the ammeter has no resistance, so you don't need energy to pass it, and then you reach here, the voltage here is also 10 volts. And because there are no electrical components between this point and this point, the potential here is also 10 volts. And on the right side, if it's 0 volts here, we can see that there are no electrical components, so this point here has to also be 0 volts, and this point here has to also be 0 volts. So what's the difference in potential for the middle branch, this branch here? It's 10 minus 0 is also 10 volts. And how about for the one at the bottom, this bottom branch, 10 minus 0 is also 10 volts. So basically the takeaway is that the potential difference is the same, is equal across each branch. So this branch and this branch, they have the same potential difference. Okay, and finally complex circuits. For complex circuits, the idea is the same, it's just that you can have parallel components in series circuits or series components in parallel circuits. The first example here, this is a parallel circuit in series with another component. So this part here is in parallel, but the parallel part is in series with the rest of the circuit. Right? So if I were to redraw this thing, it would look like this. And here, here, here. Then you see this big component here. If I compressed it into one, it will just be this part here. Okay, so the purple part is in series with the rest of the parts, the yellow parts. So this is the purple part, and the rest of it is still the yellow part. And the next example is here, having a series branch inside a parallel circuit. So if my yellow part was my series circuit and my blue part was my parallel circuit, you can see that the yellow part is in parallel with the rest of the circuit. So to redraw this diagram, it will look something like this. And this middle part here is yellow, is the yellow part here, right? So why do we need to do this? It's because given a parallel circuit, we know that the potential difference is going to be equals to the EMF. So the potential difference across this branch is going to be equal to the EMF. So to do your relevant calculations, it's easier to look at it like this. And same thing for before, in a series circuit, the current is the same. So the current across this whole thing will be equals to the current in the rest of the circuit. But if we looked at it as a parallel component, then the current here and the current here would be different. So we won't be able to relate it back to, say, this current. But this current is equals to the sum of this current, which is over here, the current here.